You guys need to come in and if you missed it, okay, sometime this week, Monday, Wednesday, take it today after school or Wednesday after school is fine, okay? But you need to come in and make it up because I'm hoping to have it back to you guys by Friday.
Yes.
Okay? Because next Friday is the next test. Okay? Yeah.
That quick.
So what's nice is we're gonna get caught up. What I have planned is, okay, so April 5th, which is next Friday, is the test. And then the next unit, which is the last unit, we're gonna be done, like it's quick. We're gonna be done on the 12th. We're not gonna be done on the 12th. I'm sorry, this is spring break. Okay, and then we only have one more lesson when we come back on spring break and we'll be done.
And
then we'll have a test on that unit, yeah. I want to give a test on this because I haven't given a test till after the AP exam on this, and I think it's hurt people because the fact of studying for a test gets you to learn it better. And so we've been missing these types of problems on the AP exam, but I think it's because I've been putting off giving a test so we have more days to review. I'm going to give you a test on this before the AP exam, okay? Because it just makes you concentrate and like learn how to do that really well, okay? All right? So, yeah, we'll be done. Okay. Yeah, this unit, one more, and that's it. Okay? Then start reviewing for AP exam. Okay? Anybody else need the notes?
Are you recording it? He still records that.
Boy. You're gonna need the books. You're gonna need the books. Well, because this won't take very long. I know you do. Yeah. Put them on the, because they're in the way, right? Yeah.
It's not quick, then. Maybe.
Okay. Some of these problems are going to be a little frustrating for you. I totally get that. You just got to kind of persevere, okay? A little bit, okay, today. And there's going to be a technique that I show you in a couple days that will start to make sense, okay? And it'll make the thought process a little bit easier, okay? But today is the 25th. Okay. If y equals 3x squared plus 5, then dy over dx has to equal 6x, right? Yeah?
Yes.
Okay. So if I try to go backwards, okay, and anti-differentiate this, I would get 3x squared, and I wouldn't know it was 5, right? Okay. 3x squared minus 4. dy over dx is equal to... Again, if I had to differentiate this, I won't know that there was a negative 4 involved, right? I will know there's a possibility of having a constant, but I wouldn't know it. I know for sure we'd have a 3x squared, though, right? Okay? Y equals 3x squared plus 7. dy over dx is... Okay, so these are called differential equations because they're derivatives. Differential equations, okay? What was the function that they came from? Okay, and that's called solving a differential equation. So all of these differential equations came from the same differential equation came from 3 different equations, right? Okay, so we don't know which one it came from specifically, okay? So when we do this, it's called the general solution, okay? Which would represent all 3 of these, okay? So here's a derivative, dy over dx is equal to cosine of 3x to the 5th times 15x to the 4th. Okay, so we're going to write dy over dx is equal to cosine of 3x to the 5th times 15x to the 4th. And what we're going to do is we're going to multiply both sides by dx to get dy by itself. So dy is equal to cosine of 3x to the 5th times 15x to the 4th times dx. Okay? And then to get y, what we're going to do is we're going to take the integral of both sides. So the integral of dy is equal to the integral of cosine of 3x to the fifth times 15x to the fourth dx. Here, okay, so here's where this is how we deal with products, okay? If we can't multiply them out, like we can't multiply these, right? Yeah? We can't. Okay, you cannot do it, okay? So when you cannot do it, what you have to realize is that this product came from the chain rule. I won't give you one that didn't come from the chain rule, okay? This came from taking the derivative and using the chain rule, okay? Where did this 15x to the fourth come from? The derivative of 3x to the fifth, because right? They match up, right? And you're going to see this on the homework, okay? Okay, so the integral of dy becomes just y plus some constant, right? But over here on the right side, we're going to also have a constant, right? All right, so what we're going to do is we're just going to combine them and make one big constant, okay? So we're not going to worry about putting a plus c on this side. We're going to put a plus c on this right-hand side, okay? Okay, so this, you got to realize this 15x to the fourth came from taking the derivative of 3x to the fifth, right? Okay, and then what had to have been the function that we took the derivative of? What was the outside function of this chain rule? Well, the derivative is cosine. Had to have come from, because the derivative of sine is cosine, and we'd have to take the derivative of the inside, right?
Yeah.
So this came from y is equal to sine of 3x to the fifth plus c, right? Okay, and this right here is called the general solution. Okay, you can always check your work by taking the derivative of this. So if I take the derivative of y with respect to x, that would give me what on this side? dy over dx. If I take the derivative of this, it would be cosine of 3x to the fifth times 15x to the fourth, right? Plus the derivative of a constant is, so we don't need to write if it's plus 0, right? So you can always check. Everybody okay with the general solution? Because the derivative of sine is cosine. So the integral of cosine would have to be sine. Okay, so today, this is what's going to be kind of weird. It would be helpful for you, I think, if you think of, instead of thinking of the antiderivative rules, you think of, okay, what did I take, I'm giving you the answers to your derivative cards. And you have to think, okay, what did I have to take the derivative of to get that as it? Does that make sense? And that's kind of how you have to think, okay? It's still antiderivative, okay? All right? Okay. This is a different problem, okay, where I gave you specific information about x and y. What this is going to allow us to do is figure out c, which will then, therefore, give us the specific solution, a particular solution to this, okay? Like these, like the general solution to these would be 3x squared plus c. The specific one would be 3x squared plus 5, or 3x squared minus 4, or 3x squared plus 7. We can get the plus 5, the minus 4, and the plus 7 by knowing an x and a y and figuring it out. Okay? So that's what we're going to do with this one. Okay? It's really going to be the same process. Okay? I'm going to multiply both sides by dx to get dy by itself. So this becomes dy is equal to e to the x plus 8x cubed times dx. Really, we should have parentheses around the e to the x plus 8x cubed. And then what are we going to do from here? Integrate both sides? The integral of dy is y. Okay, so what did I have to take the derivative of to get e to the x?
E to x.
E to the x. Plus,
It's,
why though? What is it before that? But you're right. 8x to the
over 4.
fourth over 4. Plus some constant c.
Yep.
So that becomes y is equal to e to the x plus 2x to the fourth plus c. Okay, that's the general solution, right? That's the general one. That represents all solutions to this, okay? But we can find the specific one because y equals 0 when x equals 1. Yeah? Which means this y is 0 when all of these x's are 1. So 0 is equal to e to the first plus 2 times 1 to the fourth plus c. That would be 0 is equal to e plus 2 plus c, or negative e minus 2 is equal to c. So I'd have to add that to my equation to get the particular one, right? So it's going to be y equals e to the x plus 2x to the fourth minus e minus 2. Are you okay? The difference is you're just plugging in x and y and figuring out what your c is on these, right?
So if we get a whole number, do you want us to write that? Or we always
Like
do
c equals 5?
Yeah.
Yeah, plus 5. Yeah. Yeah. Okay, now, when you do this, these come along with, domains come along with these, okay? So the domain for this, there's no restrictions, right? There's no discontinuities on this, right? So what would the domain be for this one?
Negative
Negative infinity to positive infinity. Okay, so the domain for this is negative infinity to positive infinity. So we also state the domains on these. And that would be the particular solution to this differential equation. You can take a whole class on just solving these in college. Engineering majors have to take it. Okay? And it's just on solving differential equations. That's what the whole class is about. Like one whole semester class is just doing these. They're hard to do. We're doing easy ones, okay? Baby ones, yeah. Yeah. Okay. Okay, so that last curve did not have any discontinuities. Okay, when the curve is discontinuous, okay, and this is gonna be hard to understand until we actually do one, okay? The initial condition only gives a solution for the continuous pieces of the curve that contains the initial condition, and we must specify the domain. Basically, it's this. You have your initial conditions, like in this case, we have x equals pi over 4 and y equals 2. So we have all these intervals, these individual intervals for domain. Because there's discontinuity, right? So there'd be break in the domain. It wouldn't be negative infinity to positive infinity. There'd be these breaks, right? So you pick the interval that includes this. And that's how we're going to do it. And we'll talk about when we do it, okay? But that's what we have to do. So it's not going to be all of the little... You know how, like, if I say... Let me get a piece of paper. Let's say y equals 5 over x minus 3. X couldn't be 3, right? So the domain would be two pieces, right? We would say negative infinity to 3, union 3 to infinity, right? So basically what we're going to do is, okay, it can't be both those. It's the one that has the x that's in our initial condition. So like, let's say our initial condition y equals 4 when x equals 7. Then for this one, x equals 7. 7 is in this one. So that would be the piece of the domain that we choose. Does that make sense? If it was y equals 3 when x equals negative 8, then we only pick this interval. So you're only going to pick one interval for the domain. You get the idea on that? Okay. Okay, so here we go. All right, so this one right here, okay, I'm going to multiply both sides by dx to get d. We always want to get dy by itself, okay? So dy is equal to 3x squared minus cosecant squared x, and then times, and we should have parentheses around this, dx. And then we're going to integrate both sides. So this left side becomes y equals, okay, so the antiderivative of 3x squared would be 3x cubed over 3. Okay, so here's where I want you to figure this out, okay? So I have negative cosecant squared x, right? Okay, so that's the answer to a derivative, right? So what did that have to come from? What do I have to take the derivative of to get an answer that's negative cosecant squared x? Cotangent. Just regular cotangent x, right? And you just say cotangent x, so that's a positive cotangent x, right? So plus cotangent x plus some c, right? And then this one right here, 3x cubed over 3 becomes, yeah, so just x cubed plus cotangent x plus c. Understand?
Would it be negative cotan x if it was plus cosecant squared?
Yeah. Yeah. It would be plus. Yeah. It'd be minus if this was a plus, right? Okay. Because that means we had to have taken the derivative of negative cotangent. Because what's the derivative of negative cotangent x? Well, that'd be negative times negative cosecant squared x. That'd be positive cosecant squared x, right? Yeah. That's how you have to think. Okay. All right. Okay, so we can find the c. Why? Why can I find the c? Because I know y equals 2 when x equals pi over 4. So I'm going to put 2 in for y, pi over 4 in for x. So that'd be 2 is equal to pi over 4 cubed plus cotangent of pi over 4 plus c. That'd be 2 is equal to pi cubed over 64. And then cotangent of pi over 4. So you guys, you know what? We're still missing these. When I was grading these on the test, we're still missing, and we're not, a lot of us are getting them right, but there's still a few of you that are still getting these wrong. This is 1, this would be 1, and this would have to be square root of 2, because this angle is pi over. Okay, cotangent is the reciprocal of tan. Tan is y over x, so this one has to be, and my x is 1, and my y is 1, so this would be 1 over 1, which is 1. So plus 1 plus c. That would be, moving the, getting the c by itself, that would be 1 minus pi cubed over 64 is equal to c. And that's right there, that's fine for your c. If you want to leave your c as that, that's fine. I'm going to actually combine these, because what is 1? 64 over
64.
So this becomes 64 minus pi cubed all over 64 is equal to c. I'm okay either way you want to write c, you do it either way. You write it with 1 minus pi cubed over 64 or this one. It doesn't matter to me, okay? It doesn't matter to me, okay? Okay, so now what we know is that y is equal to x cubed plus cotangent x plus 64 minus pi cubed over 64. Or you have right here, instead of 64 minus pi cubed over 64, you have 1 minus pi cubed over 64. Again, I do not care which way you want to do this, okay? All right? Okay, now, there are discontinuities for this, okay? X cubed does not cause any discontinuities. It's the cotangent x that causes these discontinuities. Because cotangent x is really cosine x over sine x. Cotangent x is cosine x over sine x. So the discontinuities are going to happen when sine x equals 0. Can you tell me the angles when you have a ratio of 0?
0, 0,
So x could equal 0,
pi,
pi,
2 pi,
2 pi,
3 pi,
3 pi. How about going the other way? Negative pi,
negative 2 pi,
negative 2 pi, and so on, right?
yeah.
Both ways, so on, right? Okay, so to list some of these intervals, right? Those are where the vertical asymptotes happen, right? Okay, so to list these, we would have negative 2 pi to negative pi to 0, 0 to pi, pi to 2 pi, and so on, right? So it's not, the domain is not going to be all of these. It's going to be the one that includes our initial condition. So what's our initial condition? It was x is equal to,
pi over 4.
so of these, which one includes pi over 4?
0 to pi.
That's going to be our domain. So to answer this question, the particular solution to this is y is equal to x cubed plus cotangent x plus 64 minus pi cubed over 64, and the domain is 0 to pi. And that's our answer to this. Are you okay?
And we're not gonna have brackets, right? Or will we?
I don't think so. I can't think of, off the top of my head, I can't think of a situation where you'd have them. That doesn't mean you wouldn't.
So we
All right.
have two plus functions and then somehow have two.
Yeah. I have to look. This is gonna come into play more in a few days, more so than it does just today. Okay. You good? Okay, so we were able to do this because we're able to do antiderivatives. Okay? What if you can't do antiderivatives? Okay? So if you're not able to do find the antiderivative, we can use the fundamental theorem of calculus. Okay. Now, I want to say this, okay? This, if we go the integral from a to b of f of x dx, remember what the fundamental theorem of calculus says? This is capital F of a, the antiderivative of f, right? Which would be capital F of b minus capital F, the antiderivative of f at a, right? Yeah? Okay. Another way of saying the same exact thing, if this is the antiderivative of this, what if you start out with this? F prime of x dx. What is the antiderivative of f prime? It would be capital F.
Of x.
It would just be f of x.
Yeah.
So when you see this written like this, it's just the notation, okay? This is actually, we'd have to take the antiderivative, which is the original f, right? So this becomes f of b minus f of
Okay.
a. This right here is going to allow us to figure this out. This, along with the other fundamental theorem of calculus part 1 and part 2, we're using actually both parts for this, okay? Everybody okay?
Yes.
All right, so I know that if I take the integral from, let me back up. Let's talk about our function. Our function is a derivative, right?
Yes.
It's e to the cosine x times the square root of x minus 3, and f of 2 equals 7, okay? So when I put 2 into my function, I want to get 7 out, right? I can do that with an integral function, okay? So it's kind of something we did a while back, okay? Or a few days ago. So we're going to start this at 2, and we're going to go to x, and we're going to take f prime. But f prime is really this e to the cosine x square root of x minus 3. But we can't use x because we're using x here. So remember dummy variables?
Yeah.
So we're going to use e to the cosine of t square root of t minus 3 has to equal, okay, if this is f prime, then this would have to be, the antiderivative of f prime is f, so this would be f of x minus
Input 2?
f of 2, wouldn't it?
Yes.
I'll talk about y. Do you guys know y2 right here?
You go through.
That's my input, right? Yeah.
There's no dx or dt on it.
Yes, there is. Thank you. Yes, there is. Yes, there is. Okay, everybody good? F prime. If this is f prime, the f is the antiderivative of f prime.
Okay.
Just as if capital F is the antiderivative of f. Okay? Now, what, okay, do you guys realize I have it right now? There's f of x right there. That's the equation. That's my curve, right? But I need to move this minus f of 2 over to the other side. Yeah? Okay, so right now my f, okay, this is like saying 5 equals x, and that bothers me. 5 equals x, right? We usually switch that and say 5 equals x. Instead of we say, so couldn't we on this say f of x equals?
Yeah.
And what would f of x equals? The integral from 2 to x e to the cosine of t square root of t minus 3, I won't forget it this time, dt.
Minus f of 2.
No, it wouldn't be minus. Because I gotta move to the other side, right?
Plus 7.
Plus f of 2?
Yes.
But what is f of 2?
7.
So that f of 2 can be replaced with plus 7, and then we'll have it. Okay, couple things we gotta make sure happens. One is, if I put 2 into this function, do I get 7 out? Because that has to happen. Okay, so let's take a look and see what happens and why I picked the 2 right here, okay? And we talked about this last week, okay? If I need to find f of 2, right, that'd be 2 right here. But that tells me to put 2 right here.
It's 0.
But then that would cause this integral to become,
0.
that's why I want to start this at 2, because when I put 2 in, I want this to become 0.
So you get 7.
So I get 7 out right there, right? Remember doing this the other day? So it's coming back, right? Okay? You okay with that? Okay, so that's one of the things we have to make sure works. Does it work? Yeah. Okay. We also should make sure, okay, what if I take the derivative of this? If I take the derivative of this, I should get e to the cosine x times the square root of x minus 3. Okay, so if I take the derivative of this, it would be f prime of x. If I take the derivative of this was on Friday's test, right? If you take the derivative of this integral function from 2 to x, right? All you have to do is, because they're going to undo each other, right? And this becomes x, and this one becomes x. So if we take the derivative of this, it would give us e to the cosine x times the square root of x minus 3, which is what we have for the derivative, plus the derivative of 7.
Yeah.
And so we wouldn't have to worry about it, right? That's plus 0. And then, yeah, that's why there isn't a constant on this. So does it work? Did it give us the derivative that we started with? And does it meet this initial condition?
Yes.
Yes. You're not going to have to worry about domain on these.
Oh, that was
Okay, yeah, you're not going to have to worry about domain on these. Because there's no way for you to figure it.
Yeah.
There's just no way. No way, right? That's that class you take in college, okay? All right, to figure that one out, all right?
I'll wait 2 years for that.
You good?
Yes.
Oh.
Any questions at all?
For the last one, when we take the derivative, why do we put the x in cosine of t and the x for t minus 3?
It was that, okay, so that was back in last unit, and I showed you why back then. So it's just, to take a derivative of an integral function, all you have to do is put your x in here and here. It's basically a rule that you need to follow, right? But if it's not x, if it's something other than x, then we also have to multiply. When we take the derivative, we have to multiply by that. That's not going to happen in these problems, okay? That's where I give you this function, you have to take the derivative of it. I would ask you there, like I did on the test. Okay. All right. So it's just like that's like, okay, why? So what's the derivative of x squared? Well, it's x cubed over 3, right? Sorry, whoa, that's antiderivative. Sorry. What's the derivative of x to the 4th? It'd be 4x cubed. Why? That's the rule for it, right? So sometimes we just need to know the rule. Okay, so for this one, we just need to know the rule. How do you take the derivative of an integral function? You just take the x and you just put it where your t's are. Or it doesn't have to be t's, it could be something else. Okay? You good? That's it. Okay? So page 331, 1 through 23 odd. You can get that started.
Everyone saying the last words?
Nah.